Hello, class. So I hope you guys did well on that test that you took yesterday, and let's get moving on to the next section. It's called polynomial functions. This course is nothing but about functions, it seems like. We've got the linear functions and quadratic functions, and then we talked about, let's see, now we're going to do polynomial functions. We're going to talk about inverse functions later, and exponential functions, logarithmic functions. Each one of these functions have their own personality. It's good to compartmentalize what each one is all about, and let's get to know the polynomial function. So, here's a quick definition. By the way, this is Math 1220, polynomial functions. So a polynomial function is powers of x, if that's the variable being used, being added or subtracted with whole number exponents. And what do I mean by whole numbers? Whole numbers are this set of numbers. 0, 1, 2, 3, ... So that goes on forever. So in other words, 30,000 would be a member of this set. It would be a whole number. These braces indicate we're talking about a set or a collection of objects. And those 3 dots there means that that pattern continues forever. Okay, so notice the whole numbers, there's no fractions or no negative numbers. Okay, so let's continue. The domain, this is always nice, the domain for all polynomial functions is always going to be all real numbers. Some examples of polynomials. It can either be a polynomial expression or a polynomial function. Here I did some expressions. Expression means something without an equal sign. So, for instance, 2x squared plus 6, isn't that powers of x being added or subtracted? So we've got 2 terms here. And isn't that a whole number, that 2? And what's the implied exponent on that x? 1. And notice the coefficients 2 and 6 are real numbers, because I did say real number coefficients. Here's another example of a polynomial expression, just like that, because again, it's powers of x being added or subtracted. Remember, terms are separated by plus or minuses. So we got 1, 2, 3, 4, 5 terms there. Let's see. How about, just to give you another look of a polynomial function. So how about f of x equals this? And with these polynomial functions, you can have as many terms as you want. So this is since I wrote f of x equals, we can call this a polynomial function now instead of a polynomial expression. And again, when you see something like this, you should be able to identify that as a polynomial function, because don't we recognize powers of x being added or subtracted with whole number exponents? 3, 2, 1, and the exponent here. That's interesting. When you have a minus 12 or a number, let me just talk about that for a moment. If I write down, say, negative 12, what's the implied exponent? Let's make it even a little easier. We'll just call it positive 12. Same idea. So I just want to show you what happens if you have a number. Before I even do that, let me talk about x squared. What's the exponent on this x? 2? And what's the degree of this x, of this term? 2. What does degree mean? Degree is the exponent on the variable. So when you have a variable as your base, the exponent and degree are the same thing. But what about if you just have a number like 12? What's the implied exponent? 1? But what's the degree of this term 12? Well, degree means the exponent on the variable, but there is no variable here. So we can get tricky here though. Isn't 12 the same thing as 12 times 1? And we haven't talked about exponents yet, but any number raised to the 0 power, this is a 0 here, any number raised to the 0 power is always going to be 1, except for 0. 0 to the 0 is undefined. So this is the same thing as 12 times 1. So what's the degree of 12? Well, degree means the exponent on the variable. So notice the degree of 12 is 0. But the exponent of 12 is 1. So that's the only nuance you got to be aware of. Otherwise, degree and exponent mean the same thing, except for when you're talking about a number. It's different. Okay, anyway, let's continue. So we said this is a polynomial function. But what about this one? That looks like one of our library of functions, a rational function. The reciprocal function, we call this 1 over x. As we recall, what does the graph of that look like? Isn't the function 1 over x, the graph look like that? Anyway, this is not a polynomial function because when we talk about exponents later, we're going to realize that 1 over x is the same exact thing as x to the negative 1. That's how we handle negative exponents. You flip over the base and then make the exponent positive. So x to the negative 1 is the same thing as 1 over x. That comes later. But now that we buy that, notice, is this exponent a whole number? No, negative 1 is not a whole number. So therefore, this is not a polynomial function. So a good lesson there is if the variable is in the denominator, it's not going to be a polynomial expression or function. So does not. What about this function here? Notice this is not a polynomial function either because of this term. Isn't that exponent not a whole number? So therefore, it's not a polynomial function. Okay, let's talk about the graphs now of polynomial functions. The graph of all polynomial functions are smooth and continuous. Smooth meaning no sharp corners, and continuous meaning no breaks in the graph. So, knowing that, let's take a look at these three graphs. Let's look at this one first. Could this be a polynomial function? Yeah, it's smooth and continuous. There's no breaks in the graph, no gaps, and there's no sharp corners. So that could be a polynomial function. What about this one? No, this is not a polynomial function because it has a break in it. It looks like x equals 0 here is a vertical asymptote. I could draw these little dots here to indicate that we are having a vertical asymptote there. So, in other words, if I start here with my pencil, I can't draw the whole graph without lifting up my pencil. As we're here, I can draw the whole graph without lifting my pencil. So that means it's continuous. Remember, no sharp corners either. What about this one? This looks like a parabola, and isn't a parabola like y equals x squared? That's a parabola. Isn't that a power of x with a whole number exponent? So that is a polynomial function. And sure enough, isn't the graph smooth and continuous? Okay, let's continue our chat with polynomial functions. We're just going to do a warm-up. More will be coming later. Okay, so a polynomial function can be in polynomial form. In other words, having a bunch of terms. I erased that t accidentally. Remember, like here, this is a polynomial function in polynomial form, because what's a polynomial mean? Terms being added or subtracted. And isn't this a bunch of terms being added or subtracted? But we should be aware that a polynomial function can also be in factored form. Notice this polynomial function right here. F of x equals that. Man, that looks wild. And isn't it in factored form? Isn't it 3 times this, times that, times that? That's what factors means, things being multiplied. If you wanted to, you could raise x minus 4 to the 4th power. First you take x minus 4, multiply it to itself. That will give you x minus 4 squared. Whatever answer you get, multiply it by x minus 4. And then whatever answer you get, multiply it by x minus 4. And then it would take a long time, though, to multiply all this out. You'd have a bunch of terms, but you don't have to. In fact, on a test, you wouldn't want to do that. It would take too long. So it's good to be aware that a polynomial function can be in polynomial form or in factored form. And in each case, there's advantages to one case over another and disadvantages. So each one has their own little charms and advantages. Like it's easier to find an x-intercept when it's in factored form. How do you solve for an x-intercept? You let y equal 0 and solve for x. So you can just use the zero factor property. The x-intercepts would be x equals 4, x equals negative 12, and x equals 6. Done. As where if it's in polynomial form, you got to factor it first and then figure out the x-intercepts. Let's continue here. Let's talk about two important vocabulary words associated with the polynomial functions. Degree and power function. I already talked about degree. Let's go to this function again. What's the degree of this function right here? All you do is search out the term with the highest exponent, and that will be the degree for the whole ball of wax. So the degree of this function, this polynomial function, is 3. It's a third degree function here. What's the degree of the second term? 2. What's the leading coefficient of this function? 8. Notice this is written in standard form. So 8 is the leading coefficient. What's the coefficient of the second term? -3. Okay, so notice it was very easy to find the degree of this function. 3. You just look at the term with the highest exponent, and that will be the degree for the whole thing. What's the degree, though, of this one? So when you're multiplying variables with exponents, you rewrite the variable and add the exponents. So remember, 3 isn't that the same thing? What's the degree of 3? Do we remember that? 0? Remember, the degree of a number is 0, because 3 is the same thing as 3 times x to the 0. So the degree of this one's 0. So 0 will not affect the sum of these degrees. What's the degree of this term, this factor? 4? What's the degree of this one? 2? What's the degree of this factor? 1? So what's the degree of f of x? 4 plus 2 is 6 plus 1 is 7. So the degree here is 7. So notice it's a little bit tricky, harder when it's in factored form, but you can still figure it out without multiplying it all out. Take the shortcut way like I kind of did. Like the first, if I were to expand this out, the first term would be x to the 4th. Okay, so, and then what's the power function? Power function is super related to degree. The power function is the leading term of your polynomial, assuming it's written in standard form, highest exponent first. It's the term with the highest exponent. So what's the power function of this function? Power function, so don't forget to write y or f of x equals 8x cubed. That's the power function for this function right here. So that's pretty simple to figure out. What was the degree of this function again? Didn't we say it was 3? So notice that the degree will always be the same as that exponent in your power function. And why do we make a big deal about the power function? Because that's the term with the highest exponent. So as x gets big, that leading term with the highest exponent takes all the credit, or it dominates all the other terms. It pretty much makes these other terms meaningless. As x gets really big and you raise it to the third power, it's huge. But if you only raise it to the second power or the first power, or if you subtract 12, that's meaningless, that stuff. So it's all about that power function. And it's easier to analyze a polynomial function if you just look at one term, the power function, as opposed to the whole function. And what happens if your power function is of even degree or odd degree? Isn't this function of odd degree? Isn't the power function of odd degree here, because isn't 3 an odd number? So what happens to the graph if the polynomial function has a power function of odd degree? So I'm going to write this down. Let me get another pen here. Bear with me, folks. And we're almost done here. Okay, so let's talk about if you have an odd degree power function. Let's do that one first, and then I'll do the even one. So what happens if your polynomial function has an odd degree power function? Just like with this function here, doesn't this polynomial function have an odd degree power function? Yes. Again, the power function is just the leading term, the whole term, coefficient and everything. So if it's an odd degree power function, think of y equals x cubed. Isn't that a polynomial function? And isn't it a power function since it's only one term? And we know what this graph looks like. It's in our library of functions. It looks something like that. And what can you tell me about the ends of the graph for y equals x cubed? Or for that matter, any power function which is an odd degree. The ends go in opposite directions. through the first and third quadrants. So that's good to know. That's very helpful if you want to get a rough sketch of a polynomial function. Look at the power function and then ask yourself, is it of even degree or odd degree? If it's of odd degree, then we know ends will go in opposite directions. Ends will go in opposite directions. That's telling a lot because, most of the graph is, as x goes toward infinity. So we know this part's going up and to the right forever, and that's going down and to the left forever. By the way, if your power function, if the coefficient is negative, the ends will still go in opposite directions, but through the second and fourth quadrants. Through the second and fourth quadrants. Okay, what about if your power function is of even degree? What happens if it's an even degree power function? I'll abbreviate here. If you have an even degree power function for your polynomial function, think of y equals x squared. Isn't that like a power function? Y equals x squared is just one term and isn't of even degree. And we all remember what the parabola looks like, so it's nice to know if you have a polynomial function and the power function, or the leading term, is of even degree, then we know this. Both ends go up in the same direction. So I'm going to write that down. Both ends go in same direction, which was different from the odd degree power function. Both ends go in same direction. And they go up if your coefficient is positive. Like, isn't this a positive 1 coefficient here? What happens if you have a negative coefficient with your even degree power function? The ends still go in the same direction, but they're both going to go down, like a reflection. Okay, that was a good beginning for polynomial functions. If I'm not mistaken, I think we all enjoyed polynomial functions, and we like the personality of polynomial functions. Okay, I'm going to continue very soon in the next couple of days. I'll do another polynomial. I'm going to continue with the lesson plan for polynomial functions. Okay, good night, everybody.